Hello and welcome to Lecture 4 of Energy in Phys 1101, and in this lecture we're going to look at various forms of energy transformations, focusing on how types of mechanical energy get converted back and forth into each other. We need to start by talking about what's called mechanical energy. Now let me stress, this is not a new type of energy, it is just a category. Kinetic energy, gravitational potential energy, and spring potential energy are all examples of mechanical energy. And the thing that's important about all these types of energy that are in this category of mechanical energy is that they're very easy to transform back and forth into each other, and those transformations go both ways. And I'll just note in passing that electrical potential energy is also a mechanical energy, though we won't really deal with it in this course. So the really important thing about mechanical energies, and the reason we have this specific category for energies that are mechanical, is that transformations among these types of energies are reversible. So in other words, when you transform the energy from one type to another, you can easily transform it back. So for example, when you throw a ball up into the air, as it leaves your hand, it has a lot of kinetic energy. And when it's at the top of its trajectory and it's momentarily stationary, all of that kinetic energy has been turned into gravitational potential energy. But then as it moves back down again, when it returns to its original height, all of that gravitational potential energy it gained has been turned back into kinetic energy. You can reverse the order of that. If you have a pendulum swinging back and forth, when it's at its maximum height, it has a lot of gravitational potential energy. But as it goes through its lowest point, that has all been turned into kinetic energy. And again, when it gets back up to its maximum height, that's all turned back into gravitational potential energy. And I'll just note, you might be wondering why the string doesn't seem to be having any effect on the energies. We'll get to that, but that's for the next unit of the course. One more example, because spring energy is also a mechanical energy. So when you have a mass oscillating back and forth on a spring, so let's say this is an air puck, so we don't have to worry about friction, then when it's at the maximum stretch of the spring, all of the energy is spring potential energy because the mass is momentarily at rest there. But as it travels through the equilibrium position of the spring, all of that has been turned into kinetic energy. And then once again, when it's at maximum compression of the spring, it comes to rest again, and all of that kinetic energy has been turned back into spring potential energy. Let's work an example that brings this all together. So let's suppose we have a ball, 200-gram ball, and we're going to launch it vertically using a spring with a spring constant of 100 newtons per meter. And it's not attached to the spring. We set it on the spring and we compress the spring down by an initial compression of 8 centimeters. Okay, so I've said delta L1. I'm calling that the compression of the spring at the start. And then we let go. And we can now find how fast the ball is going as it leaves the end of the spring. And we can also find how high the ball goes where it comes to rest at max height. So I'm going to start out with energy bar charts. And you should really think of energy bar charts as being just like the energy method equivalent of a free body diagram, right? You always start with a free body diagram when you're working with forces. When you're using energy methods to figure something out, you should always start with an energy bar chart to organize your thoughts. So I've set it up here in 1, 2, 3, and I've put a spot for each of the types of energy that I know should be here. Things are moving, namely the ball, and so there will be kinetic energies. Things are changing height, again, the ball. And so there will be gravitational potential energies that we have to keep track of. And we have a spring being compressed, and so we need to keep track of spring potential energies. So, initially, the kinetic energy is 0. The ball is at rest at the moment you let go of it, and so I'm just going to put a little bar down here at 0 to indicate that I've thought about that and come to the conclusion that it's 0. And I've set my axes at the initial location of the ball. That's my choice. We'll talk about that more in a little bit. But that means that initially the gravitational potential energy is 0. And then the spring is initially compressed, and so there must be some amount of spring potential energy at the start. So time 2. So now the ball is in motion, and so there is now some kinetic energy in the system. The ball has also moved up somewhat from where it started, and so there's some gravitational potential energy in the system. But at this moment, the spring is now at its equilibrium length, and so there is no spring potential energy. And finally, at time 3, now the ball is at rest again. It's at its maximum height, so it's momentarily at rest. It is up as high as it's going to go, and so we have a lot of gravitational potential energy. And the spring is again uncompressed. And you might worry that the spring might have oscillated back and forth, but if the spring is unable to do work on anything, it has no energy. And if it's not attached to a mass, then it has nothing to do work on. And so when there's no mass on a spring, it has no energy. That is approximating the spring itself as massless, and most of the time we can get away with that. Okay, so there's our situation, and we could now start thinking about solving for things. So we know the most about time 1, and we can then use conservation of energy to connect time 1 with times 2 and time 3. I've been careful to draw these so that the heights of these bars all add up to the same thing. And as you're thinking through energy bar charts, it's often a good idea to do that because it helps you clarify your thoughts. But the main idea we're going to use here is that the energy is conserved. So energy at time 1, this is the total energy at time 1, is the same as the total energy at time 2, and it's also the same as the total energy at time 3. And notice that I can use this to connect any pair of times. So for example, if all I cared about was time 3, right? If I just wanted to know how high the ball went, I wouldn't have to figure out how fast it was going as it left the end of the spring first. I could go straight there because I can write that energy 1 is equal to energy 3. So maybe I'll do that first. Let's find how high the ball goes first. And so I'm going to write energy 1. Okay, so energy 1 is US1. That's all that's there. And that equals energy 3, which is just UG3. And you see, all I'm able to do is use the energy bar chart to write my conservation of energy equation. You can really think of it as that there are plus signs in here and equal signs in between the times. And so this is just a picture of the conservation of energy equation for this system. So now I'll just plug in the different expressions. A half k, and I'm going to call this delta L 1 squared. That is the compression of the spring, and that equals mgy3. And so I can easily solve for y3. Plug that into your calculator and get an answer, and I will too. And so we find that in the end, the ball winds up 0.16 meters, 16 centimeters above where it started, or rather above the axes, but that is where it started, which means it's actually only 8 centimeters above where the end of the spring winds up. Okay, so now if we want to know how fast the ball is going as it leaves the spring, we can do that again, but use times 1 and 2. So I'm going to go ahead and write time 1 is just US1. Time 2 is a little more complicated, right? Because we have a kinetic energy and a gravitational potential energy there. So K2 plus UG2. And again, I'll just write this all out. A half K delta L1 squared equals a half M V2 squared, that's what we want to solve for, plus mg y2. And I'll note that y2, what is y2? Well, it's how high the ball is at this moment. And the axes are down here where the ball started, 8 centimeters below the equilibrium position of the spring. So the ball is at a y2 of 8 centimeters. y2 happens to be equal to delta L1. So you can now solve this for V2. So I'm going to solve it for V2, and you go ahead and do it at the same time. And I've got 1.26 meters per second. And that's pretty slow, but note, it only goes another 8 centimeters after this, so it makes sense that the ball wasn't going very fast. Just take a moment, check the units, right? It's good when you're dealing with expressions you've never seen to check the units. Newtons, kilogram, meters per second squared, all divided by meters times meters squared all over kilogram meters per second squared. So kilogram meters per second squared, take out kilogram meters per second squared. 1 over meters, take out one of those meters, and this comes out to meters as it should. Do the same down here. Check these units, make sure it comes out as meters per second. Well, it's been at least 5 minutes since we've thought of throwing a ball up into the air, so, clearly it's time to do it again. And this time we're going to use it to answer a really important question, and it's going to keep coming up all through this course and, in fact, through Phys 1201, because it's important for thinking about voltage. And the question is, where is potential energy 0? Well, think about it. When I set my axes, I'm defining where the gravitational potential energy is 0. And so if I move my axes, then I've changed what the gravitational potential energy is, and I've changed where it's 0. But if you think through what that does to the conservation of energy equation, all it does is add a constant amount of energy to each side of the equation. And you can always add something to each side of an equation, and the equation remains true. So it doesn't change anything. So the point here is that you can set your axes any way you want, and so potential energy is 0 wherever you say it is. There's no right or wrong answer. And I've used gravitational potential energy to explain this, but this actually applies to any type of potential energy. So the reason it's so important to distinguish between mechanical energies, which can transform back and forth from one form to another easily, and other forms of energy, is that this doesn't apply with other forms of energy, and in particular, thermal energy. So we've already seen that friction will transform the kinetic energy of a block into thermal energy, and in general, friction will transform various forms of mechanical energy into thermal energy. But the reverse is not true. You would be very surprised if a warm block sitting on the floor suddenly cooled down and started moving. And you would be right to be surprised, because that just doesn't happen. So transformations to thermal energy are not reversible. And this makes thermal energy fundamentally different from mechanical energy.